All right, so the first thing we should do today is take a quick look at the rules that we looked at the other day, just review them quickly, and then we'll do a bunch of practice problems just to make sure we understand how they work. So altogether, remember there were 7 of them, and we just about started to look at the generalized power rule, and we have not yet looked at the chain rule just yet. So let's go back and revisit these briefly. We started with the constant rule, which is a very simple rule. The whole idea behind the constant rule is simply that the derivative of a constant is equal to 0. And that's because, as I think I said yesterday, remember a derivative is itself the slope of a tangent line, which means that it is a rate of change. And since a constant can't change, that implies that the derivative of a constant would just be 0. There is no change. Then we move on to a really important rule. You probably remember from yesterday that we use this quite a bit. Anytime you have a term, or multiple terms for that matter, where we have x raised to some exponent, possibly with a coefficient multiplied by it, then the rule we'll use works as follows. You notice that we'll write this as x is raised to the nth power, and k is the coefficient in front of x to the n, which could be 1, by the way. And so what will happen is when we take the derivative, we're going to multiply the entire expression by the exponent n, keep the constant k, and then the exponent to x is reduced by 1. And that's all there is to it. It looks very messy, but it really isn't that difficult. So whatever your number is, you start out with some value. Let's say, for example, f of x is 3x to the 5th. Then here's your k, here's your n, and that implies that f prime of x, which is n k x to the n minus 1, equals 5 times 3 times x to the 5 minus 1 power. Ultimately, that reduces to 15x to the 4th power. So polynomials, any polynomial you might encounter, its derivative can be taken with just these 2 rules, the power rule and the constant rule, because that's all you'll need. Okay, so, but we'll see the power rule quite frequently. All right, let's see, what else did we do? The rule for sums and differences. This is a very straightforward idea. If f of x is simply a sum of 2 other functions, g of x and h of x, then the derivative of f of x, which we write as f prime of x, is the derivative of g of x plus the derivative of h of x. Or in other words, f prime of x simply equals g prime of x plus h prime of x. So that's at least a very straightforward rule. And then the corresponding rule for subtraction is exactly the same. You can see here that if I have f of x equals g of x minus h of x, then f prime of x is nothing but the difference between g prime of x and h prime of x. All right, so now let's skip ahead to the product rule. Now, this is the first one that's a little bit complicated. And it's not exactly what we were thinking. It's not like with the addition rule, where all you're really doing is adding up 2 derivatives. This one is a lot more complicated, as you can see. We have to take into account g prime, and h prime of x. All 4 of them are involved in this formula. And something like this, you really should try to memorize it because it's so important. You'll see it quite often. So this is one way we can write it. It's not the only way, but algebraically, there are other ways we can express this. But this is a common way of writing the product rule. So I'll tell you what, let's make a completely new example for this. Suppose we have something like this. F of x equals x squared times radical x minus 1. Now, algebraically, we can't directly consolidate these. Sometimes we can, like if you have a case like this. you don't really have to bother with the product rule here because you can rewrite it as 3x to the 7th and then just apply the power rule. So in that case, you would have, so when f of x equals kx to the n, f prime of x is then kx to the n minus 1. And in this case, that would mean 7 times 3 times x to the 7 minus 1, or 21x to the 6th. So you could use the product rule, but it's probably unnecessarily complicating your calculations. But this one now, the one on the left, there's not much you can do to consolidate this. So this is a golden opportunity to use the product rule. So think of this as g of x and h of x. G prime of x. Now, by the way, remember, when you have something like x squared, there's an implied coefficient of 1 here. So for g of x, you would have k x to the n, 1 times x squared. G prime of x would therefore be n k x to the n minus 1, 2 times 1 times x to the 2 minus 1, or simply 2x. How about h? Now keep in mind that the square root of x minus 1 is the same thing as x minus 1 to the 1/2 power. So for this one, where k is just 1, your exponent is 1/2, so you'll have okay, or so that's what your h prime of x is. So we can consolidate these now. So in other words, let's gather up all the information again. F of x is x squared radical x minus 1. So we have g of x, x squared, g prime of x is 2x. H of x, radical x minus 1. So even though we wrote it here as 1/2 x minus 1 to the minus 1/2, what you could do, if you prefer, is rewrite this as 1/2 radical x minus 1. Now, the rule so now we just substitute with x squared times 1/2 radical x minus 1 plus radical x minus 1 times 2x. So that's your final result. And the key thing is that first you identify what do you mean by g of x, what is h of x, calculate the derivatives, and then write out the product rule, and then make the necessary substitutions. And that can get very messy, okay, especially with radicals. They can be very messy. Now, the quotient rule is also more complicated than you might think. In fact, it's even more complicated than the product rule, because this is what the quotient rule looks like. So we have, if our, okay, I don't know what this is doing here. This should be g of h, g of x over h of x. If that's what our function looks like, then this is what the derivative looks like. That is the quotient rule. Yeah, for some reason I had copy the power rule again. Okay, so that's what it looks like. And you can see it is a mess. But what we're going to do is write out what we mean by g of x, g prime of x, h of x, h prime of x, and then just plug them in. So if we want to create another new example, let's try, oh, I don't know. How about this one? Now, in a case like this, it's possible that the denominator evenly divides into the numerator. If it does, you can go ahead and do that, and you'll end up with a polynomial, but it doesn't look like it, or we can't be sure. So if you want to check it out, you can try to divide x plus 2 into the numerator and see what happens. But if not, you might as well just use the quotient rule. So we have g of x over h of x. So g of x is 3x squared minus x plus 4. Now, in order to come up with g prime of x, we'll need to apply the product rule twice. I'm sorry, the power rule twice, and then the constant rule. So now just remembering what this stands for. If f of x equals kx to the n, f prime of x is nkx to the n minus 1. So here, we're going to have 2 times 3 times x to the 2 minus 1. Now, the x one is actually surprisingly tricky because minus x is actually the same thing as minus 1 times x to the 1. So it means the derivative nkx to the n minus 1 will be 1 times minus 1 times x to the 1 minus 1. And of course, that's 0. So the exponent is 0. And so x to the 0 power is just 1. So the final result here is just negative 1. So if f of x is negative 1, the derivative based on the power rule is negative 1. And then here you just have 0. So the derivative of g prime of x is simply 6x. Now h of x is even easier. Again, you're applying the power rule and the constant rule. And the x is, it's the same thing as 1 times x to the first power. It's just 1. Okay. So now we can plug all of this into the quotient rule. Okay, so just keep in mind that f of x is originally defined to be g of x over h of x. Okay, so remember too that we saw that g of x equals 3x squared minus x plus 4. G prime of x, we just got through showing, is equal to 6x. H of x was equal to x plus 2. And h prime of x is 1. So when we plug all these numbers in, we'll have x plus 2 times 6x minus 3x squared minus x plus 4 times 1, all divided by x plus 2 squared. All right, now it's possible that this will simplify to something nicer, but it may not. In fact, there's a very high chance that it will just be some messy expression. Once in a while, though, we get lucky. Let me just move this here so we can see it. All right, so I'll tell you, let's do this. Let's at least see what happens when we multiply these out. 6x squared plus 12x. Now here, remember, we're subtracting all the terms in these parentheses. Multiplying by 1 doesn't change anything. Minus 3x squared plus x minus 4. We have some like terms, 6x squared and minus 3x squared, so that's 3x squared. We have 12x plus x. And then we have x plus 2 squared, and we're done. If you want to, you can expand that out, but it's fine the way it is. Okay, so that's our quotient rule. Now, we just barely touched on the generalized power rule. The generalized power rule, as the name suggests, is the next step up from the power rule that we saw earlier. The difference here is that instead of x, we're dealing with a function of x, g of x. So I drew the rule for the power rule up here in the upper right-hand corner, so you can see how these two compare with each other. And the main difference is right here. This is something we didn't see earlier. So when you have a function of x raised to some power, then we use the generalized power rule, not the original power rule, or we could think of it as the simpler power rule. All right, so let's think of an example for that. So imagine that f of x is all right. Now, so this is, we're going to put it into this form. And then also, just as a quick reminder, this is the derivative. All right. Now, this one, actually, this rule could be written as well. If you had a constant, which we do here, nothing really changes, because then what's going to happen is you're going to have n k g of x to the n minus 1 times g prime of x. So if there's a constant in front of our expression, then you just leave it on the outside. The rest of the rule stays the same. So here's our g of x. This is n. Think of this as k. And if g of x equals x squared minus 4, then by using both the power rule, the simpler version of it, and the constant rule, you can see here. Let's say that we have some function f of x. Let's just look at x squared by itself. That's the equivalent of 1 times x squared. And of course, that means this is k x to the n. F prime of x is nk x to the n minus 1. And that's going to be 2 times 1 times x to the 2 minus 1, or just 2x. The derivative of the negative 4 is 0, of course. So g prime of x is simply 2x. So now I can plug everything into my formula. So let me just quickly remind you what that formula is. But something like this, again, you should probably try to memorize it. It's too important. You'll see it all the time. You might as well memorize it. Okay, so just from the last slide, we saw that n, let's see, what do we have? Three x squared minus 4 to the fourth power. The 4 times 3, this stays the same. Then here we have 4 minus 1. And then you have g prime of x, which remember is 2x. So the tricky part is that 2x at the end there. We didn't have that before. If we just had, let's say, x squared, that would be a different matter. So this is how we deal with these cases where we have not just x raised to some power, but some function of x raised to some constant power. Again, we'll get some practice with this, quite a bit of practice. Now, here's something, here's some, we didn't quite get to this point. What I wanted you to see here is just remember we briefly mentioned that there do exist what we call first, second, and third derivatives. So the first derivative is what we've been working on so far. When you take the derivative, it's called the derivative, but it's also called the first derivative because there's also a second derivative where you take the first derivative and apply the rules of differentiation to this first derivative. And then you can repeat the process and come up with what we would call the third derivative. So what we're going to do is take this polynomial and calculate the first, second, and third derivatives. And you can see we're just going to need the power rule and the constant rule because this is a simple polynomial. All right, so and by the way, if you want to see how this is formally done, remember when you take the second derivative, which is what we see here, f double prime of x is this so-called second derivative. This is the third derivative. And this is the first derivative. Usually we just say the word derivative when we mean the first derivative. But for the others, you have to specify which one you're referring to. So you can use these formulas. You can see what's happened is the formula has been applied 2 and 3 times. But you don't have to remember this formula because all you're really doing here is you're taking this result and reapplying the power rule, and this is the result. So basically what you're doing is you're taking the power rule twice for the second derivative and a third time for the third derivative. So nothing is really changing. It's just that you're doing this multiple times. Okay, so let's get this going. So the first derivative, which we've seen how to do this before, each term will be treated separately. You have 4x to the fifth, the derivative is 5 times 4 times x to the 5 minus 1. Okay. What about this one? Okay, there's 12x cubed. This one, it's going to get messy in a hurry here. Minus 15x squared. And then 7x is easy, but remember, there's an implicit 1 there for the exponent. And it's just 7. Okay, so that's our first derivative, 20x to the fourth plus 12x cubed minus 15x squared plus 7. To take the second derivative, we essentially just do the same thing all over again. We're just going to take the power rule 3 times, the constant rule once. So let's take a look at that. So up here, I've got the first derivative again. So we're going to reapply the power rule here. For 12x cubed. That's 3 minus 1. It's getting a little tight in here. And then for that last one, if f of x is negative 15x squared, f prime of x will be 2 negative 15x to the 2 minus 1. Now that's actually the first power, or just x. And there you go. And you notice the notation that we use is f double prime of x. That means the second derivative. The derivative of the first derivative is what it really refers to. And then finally, we'll do the third derivative. And again, it's just for practice. You don't see third derivatives very often. Okay, so if this is our third derivative, a second rather, the third one, we apply the power rule to each term separately, as we always do. And then for the 36x squared, (72x). And then finally, we had a negative 30x up there. Remember that 1 is the exponent. So it's just negative 30. Now, by the way, you probably would see this coming. If we did a fourth and a fifth and a sixth derivative, eventually we'll reach a point where that derivative is just 0. Okay, if you notice that these terms, these polynomials that we're creating, each time the order is smaller. Okay, here the highest exponent is 2. If we took the fourth derivative, we'd end up with a term of x and a constant. At the fifth derivative, we have a constant, and at the sixth derivative, we would just have 0. Eventually, we'll have to reach 0 when we're taking derivatives for polynomials. Now, there are some rules that we'll learn later on where this is important, but not just yet. Now, we're going to briefly take a little detour. Actually, you know what? I'll tell you what. Before we do what's coming next, let's get to the problem sets that I wanted to work on. Then we can come back to this if there's time. Otherwise, it'll have to wait. So let's see. Let's get a little practice here. Let's start with some polynomials. So now clearly we're going to, since this is a polynomial, we're going to apply the power rule twice, and then at the end we'll apply the constant rule. So for this first one, and that's because it's nk x to the n minus 1. Okay, so in other words, you always start by multiplying the 3 by the constant and the x, and then you lower the exponent by 1. Now that's for the f of the 5x cubed. What about this one? Remember, actually, there's two implied ones here. It's minus x to the 1. So it's actually minus 1. Remember, x to the 0 power is 1. Don't forget the negative sign. So that's negative 1. And then here, if f of x is a constant, in this case it's 1, then this is guaranteed to be 0. So you bring all this together, and you've got and that's it, you're done. All right. So all the polynomials are going to be very similar to this. Oops, I forgot one little detail here. All right, what's number 2? This time we have f of x, 8x to the 4th, plus 9x squared, minus 1. So it's going to be similar to the last one, not identical. So this first term, 4 times 8 times x to the 4 minus 1. Here we have 2 times 9 times x to the 2 minus 1. So we'll end up with 32x cubed plus 18x, and that's it, we're done. I don't need to write x to the first power here, although that is what it means. All right, number 3. Now this one is a little bit trickier. Now, this one could potentially be a real mess. What you should probably do is try to simplify this expression as much as possible before you apply the rules. So let's just do this. Let's distribute 3x over these two terms. So when you multiply 3x by 18x to the 4th, you get 54x to the 5th. Then here in the second term, you're going to have 39 over x plus 1, which you might want to write a little differently. It'll be easier to apply the power rule if we write it as to the minus 1. Okay, now let's look at these one term at a time. Now here, you notice how we've got x plus 1 raised to the minus 1 power. This actually could be thought of as 39 g of x to the minus 1 power. So we're going to use the generalized power rule here. So for this one, we should have a 220, no, sorry, 270 x to the fourth, which represents nk x to the n minus 1. So the first term is easy. Now, the second one, though, so think of this as some constant times g of x to the nth power. So therefore, we'll have nk g of x to the n minus 1 times g prime of x. Now, with all that being said, it's going to end up being relatively straightforward. So let's say this is our constant. N is -1. G of x is in here. Now, if g of x is x plus 1, g prime of x is going to be, we're going to apply the power rule to the x, which leaves us with just 1. And then we have the constant here. So g prime of x is just 1. So ultimately, we end up with, for this term at least, -1 times 39 plus 1 to the minus 2 power times 1. So that's the final result of the second term. So when we bring them together, now remember we had two terms initially. So this is our f of x. So we had 270 x to the fourth obtained from the power rule. And now from the generalized power rule, we'll have minus 39 x plus 1 to the minus second power. And that's it. Wow, that was a bit of a mess. We had to use several rules here, but it's good practice. Now, this next one is going to look very similar, but we might be able to simplify it a little bit better. This will be number 4. F of x equals x squared times 2 over x squared plus 5 over x cubed. Now, once again, I mean, you could use the product rule here, but you're probably better off multiplying this by each of these two terms. So you're going to have 2x squared over 2, over x squared rather, plus 5x squared over x cubed, we'll have 2 plus 5 over x, or what you could do is write this as 2 plus 5x to the minus 1. Now, obviously, this one is going to go to 0 because it's the, we're applying the constant rule, but in the second term, we'll use the product rule. And that's the final answer. All right. Number 5. Let's try this one. 4x cubed minus 2x plus 1 all over x squared. Now, this is clearly a job for the quotient rule. So first, let's figure out g prime of x and h prime of x. So based on that numerator, we'll have 3 times 4 times x to the 3 minus 1 minus 1 times 2 times x to the 1 minus 1 plus 0 minus 2. So in other words, this is just equal to 1 because x to the 0 power is just 1. So that is our g prime of x, the derivative of the numerator. The denominator is easy. 2 times 1 times x to the 2 minus 1 is just 2x. All right, so let's write out the formula, the old quotient rule. Okay, let's see, it's being stubborn with me. All right, so the rule f of x is a ratio of two other functions. Oh, sorry, that's h of x. Okay, there we go. And we'll just copy these from above. F of x was the 4x cubed minus 2x plus 1. Actually, I don't know why I'm doing this. We can just split this. It's just, this is something that if you didn't know about it, this is very helpful. If you hit the split button, you don't have to keep scrolling up and down. You can see both parts of this document at the same time. So in other words, I can see now that g of x h of x is x squared, g prime of x is 8x, 12, sorry, 12. I just had it right here. 12x squared minus 2. And over here, h prime of x is 2x. All right, now it's just a question of plugging everything in. Okay. So ultimately, we'll end up with x squared, 12x squared minus 2. All right. So I mean, we could certainly expand it, but I think this is fine. The most important thing is the rule. Okay. So anyway, so let's go on to one more. This one is number 6. Yeah, this is number 6. Very similar question. So of course that means g of x is this x plus 9, and h of x is x squared minus 7x plus 1. So now let's figure out the derivatives, g prime of x. So whenever you run into just x, the derivative of x is 1. Because using the power rule, so therefore, if this is your f of x, f prime of x is just 1 times x to the 1 minus 1 power, which is 1. Now, as far as h is concerned, using the product rule, we'll have 2x minus 7. All right, so let's go write out that rule again. Oops. Okay. And then we just plug everything in. So I have x squared minus 7x plus 1 times 1 So yes, you could continue to expand it, but this is good enough. All right, so now we can go back to the notes and pick it up where we left off, which is the trig integrals. Now you can take the derivative of a trig function, and that's what we're about to look at. Okay, yeah, so all the trig functions are back. We'll see them a lot in calculus. And so, yes, they have derivatives defined in them too. By the way, I do want to point out that in the book that we're using, I think it's still open. Yeah, here it is. If you look at the very end, there's a couple of charts here. Where did it go? We've got some of the solutions. We've got an index. Here we go. Here we go. Yes. So if you're ever not sure, and if you notice, here's our power rule. What this is telling you is that for any time you take a derivative, if there's a constant out in the front, you can just leave it out there and apply the normal rules. So that's why this is here to show you that the derivative of c times f of x is just c times f prime of x. However you obtain f prime of x, it doesn't matter. No matter what rule you're using, you're allowed to just leave the c on the outside. This is the sum rule. This is the difference rule. And here we go. Here is our, so they've written it slightly differently. They're using F and G. We're using G and H. It doesn't make any difference. It's still the same quotient rule. This one, we haven't gotten to it yet. We will soon enough. Okay, but down here, we've got our trig functions. And you can see the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative sine of x. So for the time being, we'll focus on these two. Let's see. I just want to double check and see when we're getting to the chain rule. There it is. Okay, it looks like I saved that for last. Okay, I could have moved the trig functions to anywhere in this chapter. I decided, I guess, to show them to you as soon as we're done, but with all the rules except for the chain rule. The chain rule comes last because it's the most complicated. So for now, what we want to do is focus our attention on the relatively straightforward trig functions, the sine and the cosine. So once again, you might want to memorize these. The derivative of the sine is the cosine. The derivative of the cosine, though, is the negative of the sine. You'd think they would both be positive, but you'd be wrong. Now, let's take a look at an example. Ooh, now you can see right away something's different. So it turns out this is really nothing but the product rule. You can think of this as g of x and h of x. And now we can use the product rule. There we go. Just a quick reminder, that's the product rule. So why don't we calculate the separate derivatives individually? So g of x is 5x cubed. So we will, of course, use the power rule to come up with a derivative 3 times 5 times x to the second power, which is 15x squared. And as we just saw, if we let h of x equal the sine of x, the derivative is the cosine of x. So now we just plug everything in. We'll have f5x cubed h prime of x to the cosine of x plus h of x g prime of x, 15x squared. And that's it. You don't have to do anything else with it. There's really no way to simplify it. Not really. I mean, sure, you can factor it and fool around with it, but that is our final answer. All right, so now for the next example, we're going to see what happens when we use the quotient rule. So here's our function now. So g of x is clearly the cosine of x. H of x is 4x squared. So that means that g prime of x is the negative sine of x, because we just saw that a minute ago. That's right there. And that also means that the h of x, we can calculate that with the product rule. 2 times 4 times x to the 2 minus 1, or 8x. Now we just plug everything in. All right, so it's already been done here for you, but let me just quickly remind you that g of x was the cosine of x. G prime of x is the negative sine of x. F of x was 4x squared. And f prime of x is 8x. So you can see that we've plugged everything in. Oh, wait a minute, hold on. I just realized I've mislabeled it. These should be h's over here. Now that's better. Okay, so in other words, you can just copy these up here. Here's h of x. This is g prime of x. Then we have g prime of x, g of x, sorry. And then we have our h prime of x all divided by h of x squared. So this is the final result. And again, There might be a way to simplify it a little, but we'll just leave it like this. Now, if you notice before, when we took the derivatives, we only did or showed the derivatives for the sine and the cosine. What about the rest of them? All right, here we go. So the derivative of the tangent, and by the way, this is again all in the back of your book. Yeah, they're all here. You just have to know where to find them. Plus, also, if you know the inverse trig functions are here too, like the arc sine, the arc tangent, the arc secant, they all have derivatives. And down the road, we'll start to look at derivatives applied to exponential and logarithmic functions. So we'll be applying derivatives all over the place. So the derivative of the tangent of x is the secant squared of x. Now these, you can memorize them if you want to. I would say that realistically, it's really just the sine and the cosine that ideally you'd like to have them memorized. The others, you probably will just end up looking them up. Mainly because you're primarily going to be dealing with sines and cosines most of the time. Those are the ones you'll actually be using. So if you have to memorize any of them, I would memorize the derivatives of the sine and the cosine. You can do these too if you want, but it may not be absolutely necessary. Now, by the way, here we go. We're going to have a proof. We're going to see why this is true. Now, first of all, don't forget that the tangent of x is actually nothing but the ratio of the sine over the cosine. And so what we're going to do here is apply the quotient rule to come up with a derivative of the tangent of x. And so we're going to understand why this result holds. So that means g of x is here. H of x is here. So we know that the derivative of the sine of x is the cosine. We also know that if h of x is the cosine, then the derivative is the negative sine of x. And so plugging into the quotient rule, okay. Well, we're not going to have room here, so we'll do it on the next slide. I'll just write it. All right, so that's going to leave us with cosine x minus sine x minus sine x times minus sine x. Now, how does this help us? All right, well, let's find out. So here it is again. So what you've actually got here let's see. Oh, did I make a mistake? Hold on a second. Yeah, I copied the wrong thing here. Sorry, this is this is g prime of x. Yes, I knew something was wrong. All right, here we go. All right. Now here's where it gets interesting. So cosine x times cosine x can be rewritten as cosine squared of x. This is shorthand notation, by the way. These mean the same thing. And the same thing over here with the signs. Minus sine x is plus sine squared x, all divided by cosine squared x. Now, you probably think, well, we're done, right? No. There's a series of identities that are based on the Pythagorean theorem that one of which is the one we need right now. It turns out that this, for any angle x, no matter what it is, the sine squared of x plus the cosine squared of x equals 1. There's a couple of others that we'll look at later on, but these are a consequence of the Pythagorean theorem. And so that means that this numerator is just 1. Now, you also might recall that 1 over the cosine of x is the secant of x. So therefore, 1 over the cosine squared of x must be the secant squared of x. So that's why the derivative of the tangent is the secant squared of x. Okay. So now, instead of just memorizing it, you actually understand it. There's a lot of identities, by the way, with trig functions that we'll run into many of them as we go along. It's a pretty long list. If you look in the back of the book to see, it's almost shocking to see how many identities there are with these trig functions. But some of them you should try to remember, like this is another classic example. This is something that will help you out in the future. Sine x squared, sine squared of x plus cosine squared of x equals 1. That one will definitely come in handy. It's not that hard to remember. So if you're making up a list of things to memorize, I'd add this to the list right now. All right. And let's just quickly look at some of the others. Now, by the way, you can derive them all in the exact same way by starting out by rewriting cotangent as actually the cotangent is the inverse of the tangent, so it's equal to the cosine of the sine. And then you can take the quotient rule, and you'll see it does reduce to the negative cosecant of x, cosecant squared of x. The same thing can be said for the secant and the cosecant. These results are coming from the quotient rule or the product rule, as the case may be. So, but you can see what I mean about, nobody expects you to memorize these. You might want to remember the derivative of the sine and the cosine, but these, maybe not. Okay. Especially in this day and age, the calculator should be able to help you out with this. Now, what if we had something like this? Oh, no. Well, we've got a couple of different rules going on here. We have the addition rule. So if you think of this as g of x and h of x, that means that f prime of x is the derivative of the first term plus the derivative of the second term. If the second term is a product, it will require the product rule. Okay, so it's not that messy, but we'll need to consult with that list of derivatives in order to do this properly. So for example, the first one we saw before, the derivative of the cosecant is the negative cosecant times the cotangent. So we got that one out of the way. But this term, x tangent x, we have a product rule. So we can think of this as and then, of course, g is x, h is tangent of x, the derivative of x is 1 from the product rule. And as we saw in our chart, the derivative of tangent x is, in fact, this is the one we proved, is the secant squared of x. So that means that just for this x tangent x, we have x secant squared x plus tangent x times 1. So now, don't forget, we previously had this first term. So we're going to combine them now. And we end up with, okay, this is the one we just derived with the product rule. Actually, it's been consolidated a little bit here. If you notice, no, it's fine the way it is. That's right. Okay, and then the first term, remember, we saw that the derivative of the cosecant is this, negative cosecant times cotangent. So when we combine everything, here's our final result. This is everything, okay? So this was the derivative of the first term, which was cosecant x. And this is the product rule applied to x tangent x. And we're done. Okay. Now we're ready to start. Like I said, this is a fairly complicated idea, this notion of the chain rule. Actually, the generalized power rule that we saw earlier is a special case of this chain rule. So this is an awfully important concept. We're going to see it all the time in calculus, but we need to sort of build up to it and try to explain it properly. It's a little bit more involved than the others. So we're going to do that next. And then we'll get some more practice. We'll try to get as much practice as we can, but the next major topic here is the chain rule, and it's a very important one. So we'll stop here, and next time when we pick it up, we'll be looking at the chain rule. Okay, so I'll see you next time.